understood.
Okay, good afternoon, everybody. We are here in our 57 section of this seminar for partial differential equation and applied mathematics. And now, today, we have two great professor here. It's our pleasure to receive here today Professor Shu-Ming Sun from Virginia Tech, who will introduce by Professor Roberto Capistrano. And then in the continuation, we have Professor César Nietzsche from Federal University of Rio de Janeiro that will be presented by Professor Mauro Rincon. So nice, it's a good, nice to have you here. And Roberto, the stage is yours. Thank you.
Okay. Hi, everyone. Good afternoon. It's a pleasure for our seminar to welcome Shu-Ming Sun, professor at the Department of Mathematics of Virginia Tech. Professor Shu-Ming Sun will talk about the solitary waves or multi-solitary waves on water waves. Just let me tell you a little bit about Professor Shu-Ming. Professor Shu-Ming started his career in the 90s when finishing his PhD thesis at Wisconsin under the supervision of Professor Meng-Xiang Chen. Shu-Ming Sun is an expert in exact theory of the existence and stability of surface wave, as well as Shu-Ming working well positioned for the initial boundary value problems for some models equation arising from water waves. Okay, like a KdV, Schrödinger, Benjamin-Bonner-Mahon equation, and KP equation, etc. He visited several universities until become a full professor at Virginia Tech in 2002, with more than 85 publications between articles and books. Professor Shu-Ming has around 1,000 citations of MathSciNet and 5 PhD students. Today, Professor Shu-Ming will give us this great opportunity to attend his lecture, Exact Theory of Solitary Waves or Multi-Solitary Waves on Water Finite Depth. Thank you, Professor Shu-Ming, for the nice opportunity for us. Thank you.
Okay. It's my turn now?
Yeah.
Okay, good. Okay, so first of all, I would like to thank organizers of this seminar to invite me to give a talk here. And as I said before, and this is the first time since the pandemic to give a talk now on the Zoom. So I think that I hope that the life will become better and better, and we can have the face-to-face talk later. All right. So today, the title of my talk is Exact Theory on Solitary or Multi-Solitary Waves on Water of Finite Depths. So the solitary wave theory has a long history. It's a really long history. So I will give you a general introduction of this exact theory on solitary waves. So it's called exact theory. So we will see that later. All right. So first of all, let's discuss the physical problem we are going to consider. Okay. So first of all, and here we have a layer of fluid. So this is the layer of fluid. Okay. And the fluid at infinity is the depth of the fluid at infinity is h, and the rho is the density, and g the gravitational acceleration constant. And we have free surface. So free surface separates air and fluid. On the free surface, and we have a wave moving with a constant speed c. So I call it Cp. Okay. And also on the free surface, we have surface tension. And the capital T is the surface tension coefficient. So for this problem, we are interested in traveling waves moving on the free surface. And we assume that this fluid is inviscid and incompressible, and the fluid is in rotation. So now for this problem, in order to study this problem, and we have two non-dimensional constants. The first one is called floor number. The floor number is given by Cp divided by square root of GH. Okay, so H is the depth of the fluid at infinity. and another called a bound number, which is so-called non-dimensional surface tension. And this is denoted as tau. So tau is capital T, which is the surface tension coefficient divided by rho, the density, h squared g. Okay, so these two constants are very important to determine the traveling waves on the free surface. So this problem was first studied by Scott Russell in 1834. And when he did an experiment to determine the most efficient boat, canal boat, so he discovered a phenomenon that he described as a wave of translation. So this story has been told many, many times. Okay. And in the fluid mechanics, this kind of wave is called Scott-Russell solitary wave or solitron. The discovery of his discovery can be described as follows. So he said that I was observing the motion of a boat, which is rapidly drawn along a narrow channel by a pair of horses. When the boat suddenly stopped, not so the mass of the water in the channel, which had put in motion. It accumulated round the prow of the vessel in a state of violent agitation, then suddenly leaved behind, roll forward with greater velocity, assumed the form of a large solitary elevation. Okay, so he observed the largest solid of elevation, which is moving up along the smooth and well-defined heap of wave, and which continue its course along the channel apparently without the change of form or diminution of the speed. So he said, okay, I followed it on the horseback and overtook it, still rolling on at about the rate of some 8 or 9 miles per hour, so about 14 kilometers per hour, so it's pretty fast actually, and preserving its original figure, some 30 feet, or which is about 9 meters long, and a foot to a foot of half, which is about 300 to 450 millimeters in height. So its height gradually diminished after a chase of 1 or 2 miles, about 2 or 3 kilometers, and I lost it in rhythms of channel. Such in the moment of August 1834 was my first chance interview with that singular and beautiful phenomenon which I have called the wave of translation. Okay, so that's what he described in his paper. And then later on, he did experiments in his backyard and made the further observation of the property of this type of waves. So of course, this is the wave tank. So first one is the wave tank here. Okay, and then the left end, he pushed the left end of the wave tank, and of course, this will give some elevation of the water on the left end. Then you can see that a solitary wave suddenly moved to the right, okay, and with constant velocity. And he also did like drop a like iron block, okay, to the water, and you can see that immediately. You can see that you have the solitary wave moving with a constant speed, actually. Okay, so he did several experiments, and you can see that if he pushed the right end very further, and you can see that you have 2 solitary waves coming out. Okay, one is here, and another is here. You can see. Okay, so the conclusion of his experiments is like this. Okay, so somebody's okay. No, nobody. Okay. So conclusion of his experiment is this: waves are very stable and can travel over very large distances. And normally, in general, of course, at that time, people always think that the normal wave would always tend to either flatten out or steepen and top it over. Okay, so it's called a wave breaking. Secondly, he conclude that the speed depends on the size of the wave and the depth of the water, or actually it's called F, the floor number, which we defined before, and the F is near 1, basically. And thirdly, and unlike the normal wave, they will never merge. Okay, so a smaller wave is overtaken by larger wave, then just moving on by themselves. Okay, rather than they combine each other. And if the wave is too big, for the depth of the water, it is split into two. One is bigger and one is small. So this is the main conclusion of his experiments. But wait a minute, why doesn't move? Yes, here we go. So at that time, people don't believe that because his experiments is at contrast with the Newton or Bernoulli's theory of hydrodynamics. And at that time, Airy is, of course, is a very famous mathematician, and also Stokes, the Stokes, right? And they both had difficult to accept the Scott Russell's experiments because Scott Russell's observation could not be explained by the existing water wave theory. Okay, so they strongly against these experiments. They said something's wrong there. Okay, and they just don't believe that. Then in 1876, Rayleigh published a paper, and he used the formal derivation to support, formal argument actually, to support the Scott Russell's experiment. And then finally, in 1871, and Scott the Busniewski first gives a mathematical treatment, a very theoretical treatment, to validate the experiments, and he showed that this sort of will exist theoretically. Okay, so by that time, of course, Scott Russell's observation on solitons were accepted. Okay, then it comes to the KdV equation, which is Cordova-Gervais, and in 1895, Cordova-Gervais published a paper on solitary waves, which was a very important, of course, milestone in history of the development of solitons theory. And they formally derived a first-order model equation for the free surface. So if the free surface is determined by 1 plus this mu here, and u can be written as epsilon. Epsilon is a small number, and c epsilon to the 3/2 t and 1/2 epsilon 1/2 x. Okay, and here h is the one we already normalized everything. Then this c will satisfy this famous equation, and later on it's called the Cordova-Gervais equation. Okay, or KdV equation. And they needed the so-called long wave assumption of the exact equations, and the exact equation is called Euler equations. And here you can see the floor number f to the -2 is equal 1 plus lambda 1 epsilon. Okay, so lambda 1 is here. Okay. And here epsilon is positive, is small. And actually, at that time, Busniewski in 1871 already had this equation, but he put it into a footnote, and people did not notice that. Okay. And then for this KdV equation, the Cordova-Gervais equation, and they also found the traveling wave solution. So that's the traveling wave solution. Okay, and it's a square solution. So the free surface looks like this. Okay, so that's from experiments. So you consider this when you're traveling x minus ct. So they found the traveling wave solution, which we now call the solitary wave solution. So is it? And then there are a lot of numerical computation for the solution of the KdV equation. So of course, KdV equation was derived a long time ago, like in 1895. But the full development of the solution of the KdV equation is around like the 1960s, when people using modern digital computer to study the other solutions of the KdV equation. Then you got a lot of soliton wave theory and a lot of like applications. Okay, so this application includes like the physics, electronics, biology, and fiber optics. Okay. And they also like the plasma physics, nonlinear optics, tomatoes, and the great red spot of Jupiter. Okay, so there are a lot of many applications after that. And then they also had like the park, which this park is in the Netherlands, and you can see that if the wave like it can be generated at the one end, and then you can see solitary wave moving along this water tank. Okay, small water tank like a channel. Okay. Okay, so they really consider the motion of the solitary wave. And then this picture is in I think in Science, okay, and published in 1999 or something like that. So this is the channel which the Scott Russell observed the solitary wave exactly. Okay, is that the same spot actually? Okay, and they built a platform there and they did the experiments. And the first time in the conference, was in like in 1981 or 82, and they tried to generate the solitary wave on this channel, and they hired like several like graduate students to push a boat, but they are not successful. They were not successful. Then later on, in 1991, they had a boat. You can see a steamboat, okay, or gas boat. It's a boat, and then they use the boat, and then you can see that the solitary wave is generated. Okay, so you can see that amplitude is pretty high actually. It's a long wave. Okay, and then of course this is the story of the solitary wave. The discovery of solitary wave and all the development afterwards. Okay, Okay. So now we are mathematicians and we want to have the mathematical question. So question is this: is this traveling wave or solitary wave of the KdV equation an approximation of the solution of the exact nonlinear equation, nonlinear governing equations? Okay, right? Because the KdV equation is just the approximation. Okay, and we want to know that do we have the solution for the exact nonlinear equations which has this kind of solitary wave? Okay? So because we are considering the traveling wave solution, and we have like because we can choose a coordinate system moving with the wave at the same speed, right? So the wave is steady, okay, in this coordinate system. So in this coordinate system, and the KdV equation is changed to this equation, and this time independent KdV equation, and we have time independent solution, which is the solitary wave solution. So from this solitary wave solution, you can see that besides the floor number, and we have the tau here. When tau is what? Equal 1/3, this becomes 0, and it's just a constant. Okay. So tau equals 0, equal 1/3 is another critical value. Okay. And when tau is positive, tau is greater than 1/3, and you can see that this is positive. So this lambda1 has to be positive because of square root. So this is positive, so this is negative. So this we have started with solution of the depression. And when tau is less than 1/3, you can see that this is negative. So I need the negative lambda1. And then negative lambda1 should be positive. So we have started with solution of the elevation. So again, we have question that is this started with solution a approximation of a solution of the exact equation? So that's the most important question to answer mathematically. So let's do the formal derivation, and derivation is very, very simple actually to derive the KdV equation. Okay, so we have like the U and V is the velocity vector inside the fluid, P is the pressure inside the fluid, and of course free surface is determined by the eta, and G again is the gravitational constant, and T is the surface tension coefficient. H is the depth of the fluid at infinity. So the full governing equation without any approximation is this one. Okay. So u sub x plus v sub y equals 0. This condition is called incompressible condition because water is incompressible. And this is called a rotational condition. So we assume that this water is, the flow is irrotational. And the next two conditions are called the balance of the momentum. This basically is the Newton's second law. Okay. So right-hand side is the ma. So m is the rho is the density. Okay, so this part is the acceleration basically of the particle. The right-hand side is the force. So F equal ma basically. Okay, and because it's two-dimensional, so I have two equations. For the Newton's second law, on the free surface, y equal eta, and the first condition, which is called the kinematic condition. And this condition means that a particle on the free surface always stays on the free surface. Secondly, the second condition, P equals this one is called the balance of pressure across the free surface. Okay, so P is the pressure inside the fluid, and is balanced by what? Balanced by the surface tension coefficient. Okay, so surface tension. Okay, T is surface tension coefficient. At the rigid bottom, y equals 0, and of course the vertical velocity is 0. Of course, the particle cannot penetrate through the rigid bottom. So for this problem, and the most difficult part here is the unknown domain. The domain is unknown. So of course, you know that to study the differential equation mathematically, you need to know the domain. Okay, the domain is unknown. So domain is part of the solution. So this is the free surface, free boundary problem. So for this particular problem, and fortunately we have so-called string function. So string function at u equals the string function psi. Okay, u equals the y derivative of psi, and the v is the negative x derivative of psi. So psi is a constant on the free surface actually, and this is the well-known fact in fluid mechanics. So therefore, if we use the psi as a independent variable, the vertical variable, then the domain is fixed. So this time we use x and psi or eta as the eta psi actually, okay, as the free surface. Y equals f of x psi should be psi here. I don't know why I got it wrong here. There's this typo here. And then the psi is a constant along streamline. Then f, the y variable, y equals f of x psi. Okay, and then what? When u, the horizontal velocity is 1 over f psi, and v is negative f sub x, the x derivative of f divided by psi derivative of f. Then for this f function, which is the vertical displacement of the free surface y, can be expressed in terms of this equation. Okay, so this only got one equation now. And of course, this equation is a very nonlinear equation. And then this is inside the fluid, so psi is between 0 and 1. And then on the free surface, this is called a Bernoulli's condition across the free surface. So again, it's a very, very nonlinear equation. At the rigid bottom, psi equals 0 and f equals 0, okay? Because the vertical displacement is 0. All right, so you can see that from these equations, and you have two free constants, f, the floor number, and the tau. Tau is the here, okay? Tau is here, and f is here. F is here and here, okay? And these non-dimensional constants, tau and lambda here, will determine the solution of these equations, okay? So we call this as the exact equation without any approximation. Okay? So question is, how can we find a solution here? And the first solution is easy because you can set f equal psi as a solution. So f equal psi, then this is 0 because it's f is independent of x0, and this is 0. So f equal psi is a solution of this one. Similarly for this, okay? So F equal psi is called the steady state solution without any elevation. It's called a uniform flow. Okay. So to find other non-trivial solutions, and we assume that our F is expanded in terms of this asymptotic expansion. So psi is a uniform flow plus the perturbation. F, of course, we write this as expansion as well, lambda naught plus epsilon lambda 1. Okay. And now this is the assumption, epsilon equals epsilon to the 1/2. Okay, it's called the long wave assumption. Okay. So we plug this one into the exact equations for F, and we got the first approximation. So first order approximation is very simple. It's W1 psi equals 0. And this is the boundary condition at psi 1 and at the rigid bottom, and W1 equals 0. Okay. So for this simple equation, of course, you can easily solve the solution. Okay. And the solution can be solved by this W1 equal C times psi. Okay. So it's just plugging, and you can see a satisfied equation as long as lambda not equal 1. So that's, you can see that F must be near 1. Okay. So then to find this C here, of course, we have to go to second order approximation. So second order approximation is this one. It's non-homogeneous ODE. Okay. So this part is the non-homogeneous part, and this is the W2 part. Okay. To solve this non-homogeneous boundary value problem, and you probably know that for non-homogeneous boundary value problem, you need the solvability conditions. Okay, so the solvability condition gives you exactly the KdV equation. Of course, KdV equation has this sort-of solution. So derive the KdV equation. And you can set a free surface determined by F, right? At psi equal 1. Okay. So put 1 here and 1 here, you can see that's exactly the sort-of solution. Solitary wave on free surface. So if you are like the engineering, people think, okay, that's enough because no, you see we found a solution. But for mathematically, of course, you cannot do that because we don't know whether this or the epsilon square is small enough or not. Okay. So how can you estimate this small part epsilon square mathematically? And then so this is called exact theory. Okay. So we want to show that the solution has this form with this O epsilon squared order is smaller than the first order, of course. So this mathematical question was answered a long time ago by Levi-Lechev, Fredericks, Hans, and Biel without substantiation. With substantiation numerically, and Hunt and Van den Broek did this numerical computation in 1983. Then for large substantiation case, and Amick and Krishgessner, Sachs, Buffini, they all proved the existence of sortable solutions for Euler equation with large substantiation, which means tau greater than 1/3. For small substantiation, and Biel, myself, and Jules Krishgessner proved the existence of a sortable solution for small substantiation. Then we have an exponential tail for small substantiation. Okay, and the non-existence proof is given by myself in 1999. Okay, so for other fluids, we have a lot of research here. So the conclusion is this one: for the exact result, for tau equal 1/3, excuse me, the exact equation has this kind of sortable solution, which decays exponentially at infinity. For tau greater than 1/3, we have sortable solution of depression, which goes to 0 at infinity. And for tau between 0 and 1/3, we have sortable solution of elevation, but we have small oscillations at infinity. And this kind of sortable solution called generalized sortable solution. Okay? And then we proved that when tau near 1/3, but less than 1/3, and there is no sortable solution which decay exponentially at infinity. So this is the exact result, okay, for the Euler equations. So then let's come to the three-dimensional case. Okay, so this is two-dimensional case. Then it comes to the three-dimensional case. And three-dimensional case is this. Okay, so we add one more dimension and we have floor number same picture. Okay, and floor number defined as the same, and we are interested in the wave on a free surface. And tau is the bound number. Again, is a non-dimensional surface tension. So for a three-dimensional case, of course, the case is situation more difficult, right? And so the governing equation is this. Okay, so this the governing equation is that Euler equation. Okay? So of course you can see that it's three-dimensional, and I don't have the stream function psi, so I only can use the potential function. And this again is well known in fluid dynamics. And then the phi here satisfies the Laplace equation inside the fluid. At the rigid bottom, we have the v. This actually is the velocity, vertical velocity equals 0. So v equal y derivative of phi. Okay, and again we have two equations on free surface. This is the kinematic condition. This is the Bernoulli's condition. Okay, so similar equation, except that we have one more independent variable, but the problem is much more complicated. And again, domain is unknown because domain is part of a solution y equal eta. So we use the so-called flattening transformation. Okay, so let capital Y equal y divided by the eta, and we flatten the free surface so that the capital Y is between 0 and 1. The domain is known now. Then of course, this capital phi, which is the little phi under this transformation, is much more complicated. I even cannot write it on the equation. Okay. So for this problem, again, we can do the formal derivation. Okay. Like we did before. Okay. And I don't give you the formal derivation again now. So the result is this. And if we assume that the free surface is given by 1 plus epsilon psi, and then we got this equation. Okay. This equation is called the KP equation. Okay, KP is actually two-dimensional correspondence of the KdV equation. You can see that if C is independent of Z, I can integrate these ones for X, and that's exactly the KdV equation. Okay. And this again is approximation derived from the exact equations on the long wave assumption. And so we can see that if C is independent of Z and its KdV equation. Okay. And we have two cases. Again, tau is greater than 1/3, it's called KP1 equation, and with tau less than 1/3, it's called KP2 equation. And KP1 equation, or KP2 equation is much harder to study. Okay, so we only study the KP1 equation. And for KP1 equation, I have the traveling wave solution as well. So it's a much more complicated traveling wave solution. And you can see that this omega here is x1 is the traveling vector, traveling coordinate. Okay. And A omega is complicated and B omega is complicated. And this solution is derived by Tajiri. And of course, because it's a traveling wave, so we can choose the coordinate system moving with this wave. And this wave is steady. Okay, and we have steady KP1 equation. And we have steady solution. Okay, Sartre wave, similar to the Sartre wave solution, basically. Okay. And you can see that when x goes to infinity, okay, and this coast here and coast here, I think I forgot a square here basically, and it goes to 0 at infinity actually. Okay, and it's periodic cosine has a periodic in z direction. So we have this solution, one family of solutions for omega. Okay, so omega is between 0 and 1. When omega goes to 1, you can see that A equals 0 and B equals 0. So A, B is equals 0, B equals 0, and this goes to 0. Denominator goes to 0. Okay. So omega go to the 1 here, and the denominator go to 0 for this solution. And it's not valid. Okay. So for this solution, omega equals 0 is the KdV equation, the solution of KdV equation. When omega go to 1, and we have a very special solution, it's called the lump solution. It's a localized solution. Okay. So lump solution looks like this. So now question again is this one. Are this solution approximation of some solutions of exact Fourier nonlinear equations? Okay. So that's the question again. Okay. So basically, I don't think I have time to finish all of them. Sorry, I just too ambitious. Okay. So we have existence theory. Okay. So existence theory like this one. So it's called dimension breaking bifurcation, dimension breaking for the water wave. So we do have this three-dimensional Sartre wave solution, which is in the z direction is periodic, and in x direction is Sartre wave, like this. You can see that. Okay, so this is the 2D Sartre wave solution, which go to 0 at infinity when x goes to infinity, and plus a perturbation. Okay, perturbation as when x goes to 0 and this goes to 0, but in z direction is periodic. So we do have this solution when tau greater than 1/3. And also we do have the localized solution, which is the lump solution. Okay, so we do have the existence of the three-dimensional localized solution. So the exact governing equation has the solution like this: capital phi equal to psi, and this capital eta equals 1 plus epsilon psi c, and this capital psi and c satisfy these estimates. Okay, so this is localized because this all the Sobolev norms. Okay, so this is go to 0 at infinity. Okay, so this is the localized existence of localized Sartre wave solution. Okay, and of course this comes to the stability. So I think I don't have time to study the stability. So I think it's better to stop here. Okay.
Shu-Ming, do you have time? Okay, you
have
time. 15 minutes if you want.
Oh, I have 15 minutes. Okay.
Yeah.
Okay, I thought there's a full day.
No, you have a 50 minutes or more or less.
Okay, so I have 10 more minutes. Okay, that's good. Okay, so now we study stability now. Okay, so we have the solution. So we study the stability. So the stability of the Sartre wave solution, and the stability of the Sartre wave solution for the KdV equation is well known now. It's proved by Benjamin Bodner and many others. Okay, in 1971, 72. So Sartre wave solution is stable if you use the KdV equation. But a Sartre wave solution, stability of Sartre wave solution to the exact equations is a big open problem. Okay, it's a big open problem. Of course, you can see that for the exact equations, we only have what Sartre wave solution with tau equal 1/3, greater than 1/3, or tau equals 0. Okay, because when tau between 0 and 1/3, we have a Sartre wave solution with small oscillations at infinity. And for this oscillation at infinity, because the energy is infinity, so it's not quite realistic, basically. Okay, so we only concentrate on the Sartre wave solution for tau equals 0 or tau greater than 1/3. And for these exact governing equations, and the linear stability is very difficult. Okay, and the partial results was given by Milk in 2002, Hollywood and Shu in 2002 as well, and on certain conditions. So they need some conditions. And Lin in 2009 proved the linear instability of a large Sartre wave solution, okay, near the largest amplitude. So these are two-dimensional case, and the perturbations are restricted in 2D case. Okay. Then people said, okay, because in real world it's three-dimensional problem, right? So why we took the perturbation in 3D, okay, for the exact governing equations. So now this time we have the small perturbation of the Sartre wave in z direction. Okay, this is called transverse instability or transverse stability, whatever you call it. So, okay, so we add one more dimension now for the two-dimensional Sartre wave solution. And we proved that the linear instability problem, which means that what? We have the two-dimensional solid wave solution, eta, and we put the third dimension, z here, and we do the perturbation, okay, in z direction, okay, to the solid wave solution, two-dimensional solid wave solution. Okay, this eta is the function for two-dimensional solid wave solution. Okay. So we linearized the exact governing equations around this 2D solid wave solution and obtained the linearized Euler equation. And then we can show that this linearized 3D Euler equation around this 2D solid wave solution has a non-zero solution like this. Eta, so this chi part is this one. The zeta epsilon to the 1/2 x epsilon or e to the lambda t e to the I k epsilon z. So you can say this is periodic in z direction. Okay, so we do the perturbation, small perturbation in the z direction, which is periodic basically. And here actually this solution has this lambda. The real part of this lambda is what? Is positive. Okay. So which means that when t go to infinity, this will go to infinity. Okay, so that's why you see that it's linearly unstable. Okay, linearly unstable. Okay, because when t goes to infinity, the real part is positive, so this goes to infinity. All right, so this solution is bounded as time go to infinity, but of course this is linear instability. So how about the nonlinear instability? So nonlinear instability was proved by Rosette and Zavitov in 2011, and they showed that for epsilon small, there are initial condition. Of course, you have to do the three-dimensional case, and with distance to the 2D solid wave solution less than epsilon in the Sobolev space HS with s equal 0. Of course, L2 norm is enough, such that the L2 norm difference between the solution of the Euler equation with this initial condition and the solid wave solution will always greater than a fixed constant, okay, as time becomes larger. So they do have the nonlinear unstable. And of course, the unstable solution was constructed from the smooth unstable solution of the linearized equation. So this actually is the perturbation of this solution. Okay, so we got the linear instability theorem with this solution, and then they do the nonlinear perturbation. Of course, nonlinear equation is much harder. Okay, linear equation of course much easier, right? And they got an unstable solution. Okay, so they really proved that the nonlinear instability of the solid wave solution in 3D case. Okay, so this is for 3D case. So I think I don't want to discuss the conditional stability. So now for the 2D case, okay, and we studied the zero substantiation. Okay, so for the zero substantiation case, and we can only get the linear stability. So you can see at 2D, for 2D problem, people believe that for 2D problem is always stable. Okay, but it's a big problem and it's just unsolved problem. So we studied the linear stability first, always. So we showed that when tau equals 0 and f to the negative 2 equal 1 minus epsilon, and in the Sobolev norm with the weighted Sobolev norm under the weight e to the ax, and the linear operator, of course, because the linear problem, so I can find the linear operator a, which depend on the eta. For the linearization of the Euler equation along the solid wave solution is a C0 semigroup generator in this weighted Sobolev space. If the eigenparameter lambda with this real part of the lambda greater than this negative one, the lambda is in the resonance of this one, which means that it's no eigenvalues except at 0. Okay, and the 0 is an eigenvalue with algebraic multiplicity 2. Moreover, we have this semigroup estimate. Okay, e to the t a that's z less than this. We can say the exponential decay as long as the initial state z1 is orthogonal to the eigenspace of the lambda equals 0. Okay, so if the initial state is orthogonal to the eigenspace of for this lambda equals 0, then it's exponential decay. So this is what we call the what? This is what we call the linear asymptotic stability. Okay? If a equals 0 without the weight, then we can show that the spectrum of the operator always on the imaginary axis. Okay, so which means that the spectrum of this operator, which determines the linear stability, is on the imaginary axis. So this is called the spectral stability. So basically, this problem is for linear problem is like this is linearly asymptotically stable under the weight. If without the weight, and this is spectral stable. Of course, we have multi-Sartre wave. I think that I have 2 minutes. I don't want to discuss this one. So now we have 2 multi-hump waves. Okay, so we prove the Sartre wave solution is the single hump. So we do have the multi-hump wave, and with joint work with Dunn and Sun, myself, and in 2018 when we proved that actually the water wave went tau between 0 and 1/3, and with exact solution, exact equations has this multi-wave Sartre wave, which means that for x greater than x0, we have the Sartre wave. For x less than this x0, we have another Sartre wave. Okay, so we have 2 hump wave solutions, and this again is the exact theory. Okay, and the experiments like this, you can see that, and when Sartre wave generated, and you keep push the bottom is moving. Okay, the bottom is moving. We have hump on the bottom, and we have second Sartre wave generated like this, and then we stop the bottom. Okay, stop the bottom here, and then you can see the 2 hump waves like this moving with a constant speed. Okay, so you do have the 2 Sartre wave solution with same amplitude actually. Okay, but this is for tau between 0 and 1/3. So our ongoing project is like this. Okay, and we are doing so recently, and we studied the nonlinear stability of Sartre solution with 0 substitution using exact Euler equations. Okay, and this is a still open problem, and we'll make a small progress because we know how to formulate this problem now. So formulation is very, very hard. Okay, how to formulate this problem, and but this is still far from making any substantial progress. Okay. Okay, thank you for your attention. Okay.
Thank you, Shu-Ming, for this very, very nice review of this point of work of KDV and KP and well, whatever. Are there some questions and comments? Please everybody can put in the chat or I don't know. Juan, tá aberto o microfone? If it's open the microphone, you can say in the microphone something, questions or comments. I have just a curiosity, Shu-Ming. You work in most of KP and KDV, right? But
yep.
You can prove similar results for for example, 50 order KDV, or I don't know, the coupled system of KDV or something like that.
Yeah, KDV and KDV for people already did that. Yeah.
Oh, okay.
Yeah. KDV, yes, and they have a lot of studies on the systems. Yeah.
Yeah. Okay. Another curiosity is about the bound constant. The bound constant give some different results when you take below or above of
yeah.
this constant, right?
Yeah.
But do you have some numerical results using, in fact, these bond constants or not?
Yeah, of course, yeah. Actually, this problem is studied extensively. There are like hundreds of papers there, and they change the tau and the tau greater than 1/3, tau less than 1/3, and many much studied, because this is really like the hot area in 1990.
Okay.
Yeah, and they have a lot of like 2-dimensional, 3-dimensional numerical computation for the exact Euler equations.
Okay.
Yeah.
Perfect.
Yeah.
Well, everyone can talk in the microphone if you have some questions or comments for Professor Shu-Ming.
Yeah.
If let's see in the chat, no, till now, no. Okay, so if you don't have more comments or questions, just say thank you, Professor Shu-Ming, for this nice.
Thank you. Thank you. Yeah,
thank you very much. Yeah, thank you for giving us this opportunity.
Okay,
Sandra?
Okay, I'm here.
Okay,
Thank you. Thank you, Roberto. Thank you, Professor Sun.